let's calculate the mutual inductance of the following system of a ring. So we're going to call this our ring 1. And inside that ring, there's a very small ring here. And this one I'm going to call ring 2. And I want to calculate the mutual inductance. Now, in this problem, when we calculate mutual inductance, you have to put a current through one of the elements. And remember, M12 equals M21. So it doesn't matter which element I introduce my current, but I have to calculate the flux in such a way that it's possible. So if I were to put a current in ring 2, the magnetic field associated with ring 2 is quite complicated, and the calculation of the flux through ring 1 would be very difficult. But if I put my current through ring 1, so we'll call that I1, then we know that the magnetic field of a ring is more or less uniform. Let's call this radius r, and this radius capital R. Well, I'll call this R2, and that R1. And yes, outside of here, the field looks a little more complicated, but inside this little ring, the magnetic field is essentially uniform, and so I'm going to approximate the magnetic flux in that ring in the following way. That, remember, the mutual inductance, in this case, I'm going to integrate over ring 2 of the B field from ring 1 dot n hat dA, so this is all ring 2, divided by the current that I put in I1. And now this integral is just the integral over the ring of B1 dA2, and that's treating this as nearly uniform. This is B1. This is just B1 times pi R2 squared. And I have to divide the whole thing by I1. And that is the coefficient of mutual inductance. Now, all I have to know now is how do I get the magnetic field at the center of a ring that has a current I1, because remember, that's a very small R2, and that's our approximation. Well, in this geometry, this is not an Amperian case, but this is a classic Biot-Savart calculation that you've done before, where B1 is mu naught over 4 pi, the integral of I1 cross ds over that unit vector. We'll take our ds like that, and that is the unit vector, r hat, from S to the center P, and we divide that by R1 squared, because this radius of the ring is R1. And when you take this cross product, and if we chose some coordinate system, I hat, j hat, k hat, we get mu naught 4 pi, I1, R1, d theta 1, ds is minus k hat. Here the current is circulating in that direction. And we're crossing a unit vector that's pointing in, minus I hat. And we get divided by R1 squared. We're integrating theta 1 from 0 to 2 pi. And we have mu naught over 2 R1 times I1. And minus k hat cross minus I hat is j hat. And we'll just check our results. It all looks good. And that's no surprise, because in the center, we expect B1 to point up. And so in conclusion, we've now calculated the mutual inductance, which is mu naught over 2 R1. The I1s are canceling, times pi R2 squared. And we just check our work to make sure everything is OK. and it looks good. If I were to try to calculate M21, it would have been an impossible task. Not impossible, but I would have to know the magnetic field due to a small ring outside the ring, and that calculation is a far more difficult calculation because that field lines are really quite complicated. And so I've chosen to calculate the mutual inductance by looking at the current in I1, approximating the field at the center as uniform, and I just get the flux as B times the area. So this is a very nice example of mutual inductance of two rings that are concentric.